We haven't got to it yet.
What do you make of the fact that we now have 3 separate geometries? So you have Riemannian geometry as the parent of general relativity.
Yes.
You have Arrhenius geometry, which is based on sort of these Penrose stairs coming from fiber bundle theory, which is the parent of the Maxwell classical theory, but also the classical theory that would be underneath the strong force holding protons together, which want to repel, and the weak force, which causes beta decay.
Yeah.
All right. And then you've got this other geometric theory, which is the geometric quantum. And they're not the same geometry. So, for example, the geometry that Jim Simons and C.N. Yang find has this property called gauge symmetry. You have the opportunity for gauge symmetry in the Einstein theory. But because Einstein takes curvature and uses something called linear algebra to project all of the curvature information into a smaller subset, killing off something called Weyl curvature. If you gauge symmetrize and then project, it's not the same as projecting and then gauge symmetrizing. So the opportunity to use gauge theory is lost by the specific genius of Einstein.
Well, you see, there's a good example, because he did this amazing thing by producing general relativity. But then in his later years, he tried to develop the theory into these unified field theories, which from a mathematical point of view was not likely to give much new insights. But, he was right to think you should find a unified scheme and so on and bring one trouble is he didn't really, he considered electromagnetism, but the particle physics didn't play much of a role in what he was doing.
Well, he died before quarks were understood.
Well, that's true.
So he was innocent of SU3 and its various sins.
Sure. Yeah, that's right. I think the thing is there's huge, beautiful things in mathematics, and we like to think, and I like to think, that they do have a role, fundamental roles that we've not yet discovered in operating, the way the world works is dependent on very deep mathematics. The trouble is that there's so many wrong steps, in the sense that many beautiful things in mathematics which are guided in certain directions, which from the point of view of mathematics are great, and they can be generalizing ideas and revealing all sorts of previously unknown beauties. But the proportion of these which we find has relevance to physics is very small at the moment. Now, I think that in some ways, maybe the most powerful, the most complex numbers and the analysis of complex numbers is one example where one does seem to see a role in operating the way the world works. And I'm sure we will find other things. It's just there are so many temptations in directions which are not particularly to do with physics.
I understand that. But what I don't understand, and what I'm absolutely unsympathetic with, is that we have a lot of people who once upon a time had a lot of different ideas. Now, most of the ideas at the moment, if we're brutally honest, we are so constrained by this point in our story in theoretical physics that almost every new idea is dead on arrival unless you specifically keep it from predicting things that we don't see.
Oh, yeah.
Right. And so what I see is that you've got different, and this is a sociological and economic critique, is that you have a class of naughty boys who are very badly behaved, who get to make all sorts of claims, who talk to the press incessantly over decades about all the wonderful things they're going to do, which they don't do. And then you have got another group of people whose feet are held to the fire, where the instant they start to consider something that might, for example, violate a no-go theorem, they're roundly humiliated. Now, what I see you as having done is to carve out a very unusual niche. Twistor theory is, at a minimum, an incredibly valuable tool for generating solutions on one space from solutions on another, let's say. However, It's also somewhat tolerated within the system. It's a minority point of view. It's a minority community. But it is allowed to play a parallel game to the string world, where the string theorists have lived for years, in my estimation, on externalities. There are lots of positive externalities of having, and I do think that's the smartest community out there. I do think that in general, they're smarter than the relativists. They're even smarter than most of the geometers. They're insufferable.
Oh, they're very clever people. I
Yeah,
agree.
very clever
Yes,
people, very
sure.
insufferable.
Oh, yeah.
And the problem with that community is that it's actually accomplished a great deal that isn't of a stringy nature.
That's true. That's true.
And I do think that what they've done is they've, instead of quantizing geometry, which is what quantum gravity was supposed to be, it backfired, and they had the geometry geometrize the quantum. And that's the main legacy of these people. Is they took off for Paris and landed in Tokyo, which is very impressive as a feat, but it wasn't what they were setting out to do.
No, I think basically I agree with that. And certainly string theory has had a big influence in various areas of mathematics. But the influence directly in physics has been pretty minimal, I think.
What do you think about the legacy of something like supersymmetry, which is...
That's an interesting question.
Isn't it?
Yes. Well, it's very interesting, partly from a personal point of view, because when I first heard about it, and a lot of it was on conformal supersymmetry.
Right.
And I could see there was a lot of connection with twistor theory. The only thing I didn't like was you were led to these algebras which didn't commute, and they were, the square of something was 0 or something, whatever. I mean, they weren't the kind of algebra that you needed in twistor theory. You needed complex analysis. But anyway, I visited Zumino at one point, and I was most intrigued because I could...
This is half of the duo that came up with the sort of original deep supersymmetric model.
Absolutely, yes. And so I thought there's enough connections here, I'd like to understand it better. And yeah, I think I understood a bit more. But one thing I remember particularly, this is a little bit of a side point, but I was talking to him about two-component spinors, and I realized he was somebody who understood it perfectly well. And he told me this story. He said he'd once written a paper in which he used two-component spinors, and it worked out very well. A few months later, Abdus Salam did the same thing, but using four-component spinors. And he said everybody referred to Abdus Salam's paper and nobody referred to his paper. And he said, well, that from then on, he said he vowed never to write a paper using the two-spinor formalism, which I thought was pretty ironic, particularly since Dirac himself, it's intriguing, that a lot of people in the early days of looking at generalizing the Dirac equation and for higher spins and so on, and there were, Duffin, Kummer, and what all the ones from, I forget what they were all called, different names for all the different spins. And they were all in Corson's book, I remember. And Dirac had written this, I think earlier, I can't remember the history of which is which, but I think earlier, this paper where he did a whole lot using two spinors. I mean, Dirac using two spinors, where you see, clearly he knew about them as far as I was concerned because he'd lectured on them. But this was much earlier than that. He had this paper in the Royal Society describing all the different spins with two spinors. Much clearer, much more general, simple, systematic. And again, nobody seemed to refer to Dirac's paper, which is quite curious because there's a huge irony there because he wrote his initial paper using these four spinors and didn't realize until maybe pointed out by Van der Waals, and I have no idea where he got it from, he realized that you could write all this in two spinors. And in some ways it was simpler and use this to generalize to all the spins. But for some curious reason, nobody or very few people seem to refer to Dirac's paper.
Well, you know about this famous situation where Feynman found effectively the path integral formalism in some paper that Dirac had published in the Soviet Union.
Oh, that's right.
Right?
Yes.
And then Feynman, was trembling, I think, and asked Dirac, do you realize when you said that these two things were analogous, that they're in fact proportional? And Dirac said, are they?
You had to be careful with Dirac, because I had when I'd first written things in two spinners, and I'd written general relativity with two spinners, and I'd found certain things came out very beautifully, and this thing that everybody was worrying about at that time called the Bell-Robinson tensor.
Right.
And it dropped out if you used two spinners, and the principal null directions and all sorts of things. And the thing is, you have this equation, which is the Bianchi identity is written in two spinners. And you can see it's just the same equation that you write for massless fields. Maxwell's equations just the same. Neutrino, if it had no mass, just the same. They're just the same. You have it in the higher the spin, the more indices. But it's the same equation. And you can see it's conformally invariant, all just the same
but part of the problem that you're going to get into with all these things is I would venture to argue that even the lowly Bianchi identity, which is at the heart of how Einstein figured out how to do his equations to make sure that effectively his vectors pointed perpendicular to the orbits of the symmetries that he was considering, that we don't really even understand the things that are given to us for free fully. There's an old paper of Jerry Kasdan, I believe, in which he actually rededuces the Bianchi identity from much more fundamental principles. And the same thing is true with the sudden appearance of a version of the calculus due to Levi-Civita from merely choosing rulers and protractors. I really worry that we never actually grounded these fields properly. I don't know if you're familiar. I think it's Chekhov who said that if a gun is placed above the mantelpiece in the first act, it must be fired by scene 4. Well, for example, we have this thing called the torsion tensor.
Oh God, yeah.
That everybody's introduced to on the first day of Riemannian geometry, and then they properly are encouraged to forget about thereafter. Never really seems to show up in any meaningful way anywhere.
Well, it's always a puzzle. I know. And I've never quite made up my mind about it. Let's not go into that story, though. But yes, I don't use it, although I once wrote a paper.
But to ask you, just in terms of the path forward, it strikes me that what we have learned about our physical world and what comes up in this book is of a very frightening nature. That Einstein's equations, when you really understand them through Hilbert's insight, come from the simplest possible thing we could minimize.
Oh, yes.
Same thing for Maxwell's equations. They spread from the electromagnetism to the weak force and to the strong force because it was the simplest possible thing that could be optimized.
You're thinking of the Lagrangian,
The Lagrangian.
Yes.
I'm trying to avoid saying those words.
Yes, I know.
And then
those that know what it is.
And then Dirac's third equation, to complete this triptych, is the equation for matter which generates all of something called K-theory, which is absolutely fundamental. So I could make an excellent argument that the three major equations, to be supplemented by one for the Higgs field now that we found it, are the simplest and best possible equations of their type, not that we've found so far, but provably so.
Yes. I think the trouble with simplicity arguments, which I agree with, is that it's simple in one context, and what's simple in another context, it may be,
But nature has shown the thing that I can't get over is that her taste in mathematics, I've analogized this to raiding a jewelry store with millions of pieces and in under half a minute finding all the best stuff.
Yeah, I think I see what you mean. I wanted to finish a story, though, you see, which I didn't quite finish. It relates to something you were saying earlier, which at one point, you see, Dirac was at the same college as I was, St. John's College in Cambridge, where I was a fellow. And I happened to be sitting opposite him at one point. And I had been working on these two-spinner ways of looking at general relativity. And so I said to him, I thought something he might be interested in. Would he have opportunity to talk to me about it? So he reserved a room, and I had a little discussion with him. And then I wrote down this equation, which is this wave equation, which represents the Bianchi identities. And I wrote this thing down, and Dirac, I thought he would instantly recognize it because it's basically the same equation that he had in his paper with all these different spins. And he asked me, I wrote down the equation. He said, where does that equation come from? So I said, it comes from the Bianchi identities. And he said, what are the Bianchi identities?
Holy cow.
And I thought, well, he's been writing all these papers on general relativity and he must know perfectly what they are. The explanation, presumably, is he simply rediscovered them himself. He just didn't know they were called the Bianchi identities. I don't know. It's a very curious story.
And this was in the form that the derivative of the curvature in terms of the natural derivative is equal to 0? That's...
Yeah, in vacuum, say.
Yes.
And you take the Weyl curvature, which is all that's left of the Riemann curvature, and you write that in spinors, and it's a spinor with 4 indices completely symmetrical. And then when you write the derivative, it's the derivative acting on those 4 things in one contraction. The derivative's got 2 indices, and you contract one of those, and that's their equation. That vanishes. That's the equation. Same as the Maxwell equation, same as neutrino if you had 1 index and no mass. And it's the way I think about these things. And the conformal invariance is very crucial. That leads me to all sorts of ideas that I wouldn't have thought of otherwise. And it was clearly the sort of thing Dirac would have played with himself, because his equation, all the higher spin equations, although curiously in his paper, he did the massless case a different way, which I never quite understood why. But anyway, it's there clearly things that he understood completely. And somehow maybe never connected. I don't know what it was.
Did you read his 1963 article in Scientific American where he makes a very interesting case against naive application of the scientific method?
No, I don't. That's Dirac in scientific.
Absolutely. And his point...
I should have seen that. Yes.
He makes the point in the case of Schrödinger.
Yeah.
And he says Schrödinger would not have been led into error if he had not been pressed for agreement with experiment, because Schrödinger then, after publishing, there was a period of time where it wasn't understood that spin somehow entered the picture and complicated the theoretical prediction with its experimental verification. But I think secretly he was actually talking about himself, where he had introduced the Dirac equation. There had to be positively and negatively charged particles. And at that time, the electron and the proton were known, but the positron and the antiproton were not. Yes. And so he linked those two, and Heisenberg immediately dinged him and said, wouldn't those be of the same mass? And you're obviously making an error. And he didn't stick to his guns or have the courage of his convictions to predict the new particle.
There is something there, yeah.
And I think that 1963 paper from Scientific American is Dirac trying to give us a gift from Mount Olympus to say, stop with the insistent on the naive scientific method. Give yourself more room to imagine, more room to play, more room to be wrong.
I think that's a crucial thing. You see, that was the thing about Dirac. He just didn't want to be wrong. Now, he was very worried about saying things that were wrong. And so often he would say nothing rather than anything. So this is a big thing with him. And I think he was disturbed by... Yeah, you're right. I mean, he could have predicted instantly.
I think he needed more freedom, and he didn't have it, and he tried to give that freedom.
In a way, being too timid, yes.